let's talk about nervous tissue versus, okay, so that's sort of the end of the muscle section of the histology section. Now we're going to talk about your nervous tissue. You have two types of little, well, you have a bunch of them, but I'm just going to talk about two. You have the neuron, which I don't know, I just think the word neuron is funny. This is going to transmit action potentials, and in the form of electricity, mostly. There's some chemical there, but we're going to say that. This is what you think of. Your body is actually, there's not as many neurons as you think. Like your brain, these glial cells make up like 90% of your nervous tissue. So I'm just telling you, they're support cells. They support the rest of your nervous system. They do a lot of cool stuff, which we'll talk about when we get to the nervous system. But your glial cells are there. They do stuff. They make up most of your nervous tissue. Okay. Compare and contrast the nervous and endocrine. Okay, this is actually really intuitive if you just think about it. So I'm going to ask you to think about it. So let's put nervous right here. I'm not super good when I do this. And endocrine. Like way down here. Okay? All right. Let's start with specific. Okay, how specific is your nervous system? It's pretty freaking specific, right? It's very specific. Like, I blink my eyes. I don't twitch my whole body. I just blink my eyes. It's like that, right? Okay, your nervous system is pretty specific. It's like a neuron. It's one. It moves like, look, I can move just this finger. It's very specific. Let's think about your endocrine system. Not as specific. This is dumping epinephrine on your whole body. It actually dumps it into your bloodstream. Right? I mean, we'll talk about it's more specific than you might think, but it's not specific, right? It's dumping hormone into your body, right? So we're going to say not as specific. Not as specific. Okay. So, right? These are just like you think through them and you can get it. Okay, speed. How fast is your nervous system? It's speedy, right? It's something like 240 miles per hour. I don't remember. I wrote it. I have it in your nervous system notes, but it's super fast, right? You need to move your body. You need to move fast. So your nervous system is fast. Endocrine system. It's pretty slow. Anywhere from an hour to like several days. Sometimes your endocrine system takes to do stuff. So it's slow. It's just not as quick. What else? Duration of, okay, let's say duration of effect. Short, right? You just like, boom, blink your eye. It doesn't take you all day. It's just quick. Versus the endocrine system, where the effect of that, once you dump hormone into your bloodstream, dude, it's there, and it's going to have a long effect. Some longer than others, but much longer than your nervous system. So this gets done quick, but it's over quick. This gets done slow, but it's a long time that it works. Let's talk about control. Control of intensity, right? So how are we going to control the intensity here? This is going to be number of action potentials. So number of times your neuron fires. It can fire over and over and over, and you can keep getting the stimulus. How are you going to control your endocrine system? How are you going to control your endocrine system? The quantity of hormone. So the more hormone you dump into your system, the more intense the reaction is going to be. And let's see the type here. The type is going to be more electrical with a little bit of chemical, but it's mostly an electrical system. This is chemical. So does that pretty much sums it up. You might be able to think of some other ones, but this is fairly intuitive. It's one of those things that you just have to think about a little bit. Okay. Let's regulate ourselves, shall we? Let's regulate ourselves. I think that's a good plan. Distinguish between regulators and conformers. This is exactly what the definition says. You should, you could get this in a multiple choice without ever watching this video. But you should watch the videos because I'm saying other things that you wouldn't get. Okay, so regulators. And this is a shock. Regulate. Regulators regulate. And their internal mechanisms. Okay, that is just a mess. Let's say regulators. Internal, let's do a little one of these. Internal control mechanisms to external change. So they regulate. If the external environment changes, they regulate it. I have no idea why it's doing that. Stop. Versus conformers. Conformers who don't really do any one of those things. Allows internal condition to vary with environmental change. So one regulates, like you actually regulate your external environment. Conformers don't do that. Okay. How could you be both a regulator and a conformer? Some animals don't regulate everything. So, for example, a fish. It regulates how much salinity. So, let's say bass regulates salinity, which is salt concentration, by the way. So it regulates the salt concentration. It doesn't let the salt concentration of the water affect its internalness, but does not regulate body temp. Does that make sense? And sometimes you'll see the other. There are things that allow the salinity to go in and out, but they regulate the body temperature, for example. So you can be a regulator and a conformer, if you so choose. Homeostasis. I love homeostasis. This is basically physiology. When you take my physiology class, the entire thing is about homeostasis. Almost every lecture is about somehow how you're going to maintain homeostasis. Homeostasis is an internal balance or steady state, such as body temp, pH, the other way, come on, pH, glucose concentration or glucose concentration. Okay, so it's just you're regulating your body temperature. It's not. How do animals regulate their body temperature? Many ways. How do they maintain homeostasis? A bunch of things. So let's say this. I'm going to underline these later. Fluctuations above or below a set point serve as a stimulus, seriously, which is detected by a sensor, which is sent to an integrator, which sends out an effect or response. Okay, I'm going to underline these things, some of these things. Set point. So there's a set point. There's a set point that if it goes above or below that triggers a stimulus. It's cold, it's hot, my pH is weird, which is detected by a sensor, which is sent to an integrator, which sends out an effect or a response. Okay? We will actually probably work through this in class. I'm even going to highlight this one because I'm going to say, let's draw this out and play with this a little bit more in class, even if my voice isn't where it should be. Okay. Distinguish between positive and negative feedback. I need my handy dandy little super fun. There we go. I don't really want that one. I want this picture in your book. Don't worry, it's coming. Okay. So when, oh, come on. Somewhere there's a picture in your book. Here it is. Okay. Here you go. Picture in the book. This is really important. So hold on to yourself for a moment. And then I'll give you a break. Okay, so you have a normal body temperature, which is between 36 and 38 degrees Celsius, which you know is 98.6 degrees Fahrenheit. Your body temperature increases. So you get hot because this is running and it gets hot. So it's July and you are hot. that sends a message to your hypothalamus. And your hypothalamus, so your central nervous system is the integrator. Endocrine or central nervous system, but we're going to say central nervous system because your hypothalamus regulates it anyway. So your integrator is the central nervous system. Sends a message to the central nervous system. Dude, a sensor, like your skin is like hot, sends a message to your hypothalamus in your central nervous system, and your central nervous system sends back out a message to do something about it, right? So you should start sweating, or you should seek shade, or you should jump in a pool, or you should do something to help this situation. So, or your blood vessels should dilate because it's going to decrease their contact with the outside world. It's going to make you feel cooler. Or you're going to sweat. So one of those things is going to happen, and magically, because it's not July, it must only be like March. And this brings your body temperature back down. Okay? Let's say something else happens. Let's say you're cold. You're actually cold. Your body temperature decreases. It sends a message to the integrator. So the stimulus, there's a set point. Set points gets triggered. There's a stimulus. Dude, it's cold in here. Your skin or one of your temperature sensors sends the message to your central nervous system, which is the integrator. The integrator sends back out a message to your smooth muscles or to your blood cells, and you start shivering and your blood cells vasodilate and your temperature increases back to here. Okay? Let me tell you something crazy, just because it's fun. Okay, let's say that you are having some kind of immune, someone sneezed on you. Bad sneezing. You're sick. You're getting sick. Your immune system is like, dude, call out everyone. Your blood needs to just flow. And one of the things we're going to do is we're going to turn this puppy up. We're going to turn this thing up to 100 degrees, and we're going to be like, all right, yeah, crazy bacteria, take that. See if you can handle it at 100 degrees, you jerks. So your hypothalamus is going to raise the temperature. So your set point is now 100, 101. Let's say it's 101, right? So now your normal is 101. You're walking around with 101. Like, that's what my thermostat is set to. Eventually the bacteria leaves and your hypothalamus is like, oh, you're not sick anymore. I'm going to crank it back down to 98.6. What are you going to feel like? You're going to be freezing. That's why you get the chills, because your hypothalamus it's moving down the temperature, and your body's in this weird state of like, am I cold? Am I hot? The temperature's being turned down. It's weirding me out a little bit. That's why. Your body's going back down to 98.6, and your hypothalamus is like, no, 101, 101. And that's why you get that like weird chilling feeling. That's what that is. Okay, so does that help you distinguish between positive and negative feedback? I hope so, because I'm going to stop there. And, which mechanism contributes? I'm sorry, I didn't even talk to you about negative feedback. I don't think it gave me. Did it give me a negative feedback? Well, let me tell you what negative feedback is, folks. It's giving birth. So anytime you have a negative feedback, there's a couple of crazy negative feedback cycles. One of them is when your blood clots. One of them is when your milk comes down, when you're lactating. And one of them is when you give birth. So when you give birth, this little baby's head, this is the head, pushes on your cervix. When it does that, it releases oxytocin from your head. And that opens up your cervix. When it opens up, the baby has more room to push its little head against this space. So what happens is it also contracts your uterus and imagine squeezes it like a tube of toothpaste. It's contracting your cervix. It's contracting your uterus. It's opening your cervix, and that little head is pressing against the cervix, and that is contracting and opening and contracting, and that is a positive. So it's like, dude, this crazy contracting. For any of you who've squeezed baby humans out of your body, it's sort of an unpleasant process. And that happens until the baby's out, and it stops. It doesn't come back to a set point. It just stops it. That's the same thing with the blood clot. It keeps going until it's done and out. So it doesn't come back to a set point. So which mechanism contributes to homeostasis? Negative feedback. Because there's a set point. Homeostasis, by very definition, is a negative feedback loop and not a positive feedback loop. Okay. I'll try and get the next one into one video.